Hello, everyone. We are Physics Group 1. My name is Spencer, and I am joined by my colleagues Angela and Alexander. And today we will be teaching you a little bit about ideal gases and the laws of kinetic gas theory. So let's go ahead and jump right into it. So the whole idea between ideal gases and kinetic gas theory is to try to find some relation between gases in the world. Unlike solids and liquids, which are things that we can visually see and very directly interact with, gases are a lot more obscure, and it's a lot harder to define the relationships between these. Not to mention, gases are made of a bunch of subatomic particles, and the interactions between these particles in the universe was largely a mystery. And the first person to really put some kind of idea or some kind of law behind the relationship of gases was a man named Robert Boyle back in 1662. Who realized that there is an inversely proportional relationship between pressure and volume. So if you think about something like a container, you can, for instance, think about like a cube, and there's some gas in the cube. And if we decide to reduce the amount of volume that's in that cube, crumple it up, the amount of pressure inside of that is going to increase. Conversely, if we add more volume to the square, the pressure inside is going to decrease. And what he realized is that the product of these two values always equated to some constant, which is very strange. It didn't matter which kind of gas you used, it always equated to the same kind of constant. And so Robert Boyle believed that this was some kind of constant of the universe, that it was inherent to the way the universe worked. And much later, a man named Jacques Charles would form the second relationship of gases, which is a directly proportional relationship between volume and temperature, which also equaled to some constant, but it was different from Robert Boyle's. And he realized that if you increase the volume, you also increase the temperature in the system. The next man was Joseph Gay-Lussac in 1808, who found a relationship between pressure and temperature that was directly proportional, which equated to another constant, which means if you increase the pressure in a system, you also increase the temperature, and vice versa. If you decrease the temperature, you decrease the pressure. And finally, in 1811, a man named Amedeo Avogadro realized that there's a direct proportionally relationship between volume and the number of moles in the system. So the amount of gas. If you increase the amount of gas in a system, the volume is going to naturally attempt to increase if you keep the pressure constant. And what these people didn't know is that all of these laws were actually a part of a bigger equation. And that equation came to fruition in 1834 by a very intelligent man whose name I will not try to pronounce, who realized that the real relationship between these ideal gases, is what we're going to call them, is PV equals nRT. And more so than explaining the exact mathematical proportions of these gases, it explains the relationship between these gases. So on one side, we have pressure and volume as a multiple. And on the other side, we have the moles of gas, the universal gas constant, which is just a collection of the other constants that we got before, and the temperature of the system. So you can see everything on the same side is inversely proportional. So for P and V, if we increase pressure, we decrease volume. Same for the other. If we increase the number of moles in the system, we decrease the temperature. Everything on opposite sides is directly proportional. So if we increase the temperature on the right side, we also have to increase pressure on the left side. And this universal gas constant, as I said, is just a collection of the other constants. He found it to be something around 8.31 kilopascals over kilomoles, which is a unit of pressure over unit of moles of gas in the system. And like I said, rather than be mathematically consistent, this explains the relationship of gases. So gases being very hard to explain as they go into very extreme temperatures, whether it be super, super hot or super, super cold, this relationship is much less exact. But for ideal gases, something like the air in your room, it's very handy to have. Now I'm going to pass it off to my colleague Angela, who will tell you a little bit more about these gases and the relationship between them.
Thank you, Spencer. Okay, in this presentation, we focus on the four gas laws, starting with Boyle's law. Boyle's law, also known as Marriott's law, was formulated by Robert Boyle in 1662. What this law states is that the volume is inversely proportional to pressure at a constant temperature, meaning an increase in pressure will cause an increase in density and a decrease in its volume. In this image, the Boyle's law is demonstrated as showing that for a given mass at constant temperature, the pressure times the volume is at constant. For Charles' law was first suggested by J.A.C. Charles in 1783. This is a temperature-volume relationship. And what this image shows is that as the temperature increases, the volume increases because the faster molecules collide harder and push each other farther apart. For Gay-Lussac's law, the volume is kept constant. When the volume is kept constant, the pressure of given mass of gas varies directly with the absolute temperature of the gas. This law was discovered by Joseph Gay-Lussac in 1808, showing the relationship between the pressure of and its absolute temperature. For Avogadro's law, under the same conditions of temperature and pressure, there is an equal volume of different gases containing an equal number of molecules, meaning that fewer molecules create smaller volume and more moles. Fewer moles create smaller volumes and more moles create larger volumes. This law was proposed by Amadeo Avogadro in 1811 and was accepted in 1858. And now my colleague Alexander will present the postulates of kinetic gas theory.
Okay, so the ideal gas equation describes the behavior of gases by establishing the relationships between their macroscopic properties. To support that, equation, we refer to these 5 postulates. Now, without reading directly what they are, to summarize, gases are composed of an infinite amount of small particles. The volume of a gas includes those particles as well as the space found between them. Those particles are in a constant random motion, however, they do not gain or lose kinetic energy during collision. Finally, the average kinetic energy of the particles is proportionate to the temperature. Now, we will show a simulation of the ideal gas law in action. So, as Spencer explained earlier, you can manipulate any of the variables in the equation, whether it be the size of the box, the temperature of the box, or the influx of particles. Now, as we start by influxing a heavy flow of particles in the given space, once we start to introduce heat, the pressure will increase. And as we know, once the pressure increases, eventually it will increase so much that the lid on the given space will blow. If we were to shrink the box, still introduce a heavy stream of particles, the lid will blow much faster, sometimes even without introducing a heat variable. This was our presentation on ideal gases and ideal gas laws, and we hope you enjoyed it.